You can start. Santoro?
Okay. Let's start this afternoon, the second day of LISHEP 2021. And the moderator of this afternoon, it will be the Professor Gilson Damião. And thank you to all of you to participating to give this talk so nice today. Please go ahead, Gilson.
Okay, thank you, Santoro. Hello, everybody. Welcome to this virtual LISHEP 21 session here from Rio. If you are attendee, you can post your question using the Q&A button, or if you are a panelist, you can use the raise hand button to make any questions. I will tell all the panelists when they have 2 minutes left to finish the presentation, in case they know what time they have. And we start with a talk from Elka Caroline Aschnauer. I hope that I pronounced it correctly.
Perfectly.
Thank you. Elka earned her PhD in physics from the ETH in Zurich. And later she joined Daisy, where she became the spokesperson of the Hermes experiment. And sometime later, she worked also for the Jefferson Lab and the Brookhaven Laboratory, where she leads the HIC medium energy group. In the last year, she has been focusing on developing the science case for the new electron-ion collider and the design of its experimental equipment. So the room is yours, Elka. Have a nice presentation.
Thank you very much for your kind introduction. And I go to full screen, and I hope you hear me well and you see my slides well. So,
yes, perfect.
Thank you. It's a pleasure for me to introduce the electron-ion collider to you, which is the collider we think which will unravel all the mysteries of hadron structure. So first, I would like to introduce to you what is actually novel with the accelerator. So what is the EIC? So the EIC is actually a high luminosity polarized electron proton ion collider in the center of mass range of 30 to 140 GeV. And it builds on actually the existing facility of RIC and adds an electron machine to this, and I will come in more detail to this. What is new and different? If we kind of look to HERA, then we will have a factor 100 to 1000 higher luminosity. Both the electrons and protons and the light ions are polarized, and we have nuclear beams compared to HERA, which go from deuterium up to the highest ones like uranium. And if you go compared to fixed target facilities in EP and EA, then we have at minimum 2 decades increase in the kinematic coverage for X and Q square. And currently the facility supports 2 interaction regions, but the project supports 1 and 1 detector. And I will come to that in a little bit more detail at the end of my talk. So if we look to this, I said already, we have a hadron storage ring, which is actually based on the RIC facility. So we can run proton beams from 40 to 275 GeV. We have led to tungsten beams. We have quite high bunches, 160 bunches, so much more than we have in RIC. And that gives us actually a bunch spacing of 9 nanoseconds, which is much more than also in the LHC. We have the light ions actually polarized, both longitudinal and transverse. And we actually will kind of utilize a new concept to cool the machine, which is coherent electron cooling. And we are operating this currently in RIC and want to demonstrate first the cooling. To the hadron ring, we add actually an electron facility, which electron beams between 5 and 18 GeV. Again, the same number of bunches. We minimize the power consumption, so we limit the current. We have the beams are polarized, and we also use there a new concept which is we use a rapid cycling synchrotron as an injector, and that actually has very high periodicity to conserve the polarization from the source of the electron source into the storage ring. We have the two interaction regions, both will have high luminosity, and we utilize for the first time a really big crossing angle of 25 millirad, and that actually kind of also comes with that we have gap cavities in the detector. And if you want to read more, I give you here the link to the recent conceptual design report. So the physics which we are, the process which we are utilizing if we have EP scattering is deep inelastic scattering, which gives us the advantage that we have the unprecedented precision of an electromagnetic interaction, and we can therefore really direct model independent determine the pattern kinematics of the individual physics process. The process is governed by this kind of kinematic variables, Q square, which gives you basically the resolution power, X, which is the fraction of the nucleon momentum carried by the quark in leading order, and the matter of inelasticity. And we want to have large kinematic coverage of the machine, so from 28 to 130 GeV, because that gives us the possibility to kind of access X and Q square over a wide range in kinematics, so that we can actually probe the proton where it manifests itself as a 3 quark state at very high X, to the low X region where it basically becomes completely dominated by gluons. It also kind of the EIC, which is nice, which you can see here, it really kind of transitions between the non-perturbative regime, which is mainly covered by the fixed target experiments in deep inelastic scattering, to actually the perturbative regime, which is covered by the collider experiments existing already at RIC, LHC, and HERA, and the EIC kind of transitions nicely between both of them. So what is the science the EIC wants to kind of address? So the first one is we really would like to understand all the quantum numbers which make up a proton. So we would like to understand spin and mass of the proton. And we want, in addition, to really see how the quarks and gluons are distributed in space and momentum inside the nucleon. So we want to come, and I show you that later a little bit, really take 3D images of the protons. Then we go and do the same measurements actually at nuclei, and really would like to understand how a nuclear medium kind of changes what we measure on the proton, how the confined hadronic states emerge from the quarks and the gluons, and how actually nuclear binding is created by quarks and gluons. And then last but not least, because we have heavy ions available, so we can go actually to the densest nuclear environments and can study there whether we see basically a new state of matter, which is that the gluon densities are so high that we see a recombination and as such nonlinear effects in QCD. So if we look and take these topics which I just introduced to you and their needs in center of mass energy versus luminosity, then you can see that the tomographic imaging in 3D needs the highest luminosity, and then actually measuring saturation effects is not as luminosity hungry, but then is of course center of mass hungry. If we now look where the EIC lies in comparison with other facilities which do EP physics, the fixed target ones here, as then HERA, which has been this CERN projects with LHC and the FCCEH and then the EIC, then actually if I show you which project has polarized beams, covers the right energy range, and in addition has protons and nuclei, and the only machine which kind of combines all these unique opportunities is the EIC in the US. So how do we want to see actually kind of the mass? So we know the quark masses are kind of not making up the mass of the proton. We know the Higgs mechanism is of course responsible for the quark masses. So actually we know that most of the mass of the proton is dynamically generated by the gluons and their interactions. And that is something which we want to study in much more detail at the EIC and mapping out the gluons in 3D. In addition, we want to utilize the Sullivan process to actually study the parton distribution function of pions and kaons and see how the gluons there actually contribute to the mass. And particularly by comparing the pion and the kaons, then you can kind of see how more gluons in a small system as this two is actually contributing to the mass effects of these two mesons. So spin has been a real mystery for many, many years. We know that all fundamental particles have actually spin apart from the Higgs. We also understand by now that spin is much more than a static quantum number of the proton, and that it is not just given by the quarks and the gluons, but it is really an interplay between the intrinsic properties and the interactions of the quarks and the gluons, because we think we have also significant contribution from the angular momentum. So if you look to it, it is 1/2 that we know for sure. We have a contribution from the quarks, from the gluons, and then also of the angular momentum of the quarks and the gluons. And that is exactly what we would like to measure. So how do you do this? Well, of course, if you want to measure spin, you need a polarized beam, and that is exactly what you do. So you have your electrons polarized, you have your protons polarized, and then you measure actually equivalent to the unpolarized case, the structure function G1, which is the difference between that your virtual photon, which is emitted, interacts with a quark, which is antiparallel to the spin of the proton, or parallel, and you take the difference. And then actually, if you look to the integral over the structure function, you basically get the quark contribution. And if you look to the derivative from this distribution, then you get actually the contribution of the gluons to the spin of the proton. So here is actually what we know right now. That is the structure function plotted as function of x for a fixed q square. And you see that as soon as you come to a smaller x, like 10 to the minus 2, you see all these curves here, and these curves represent basically the uncertainty which we have on the structure function from the current data. And if I overlay here actually measurements which we can do with EIC for this x and q square bins for this q square, then you see that they are very precise. And because of this precision, we can then very nicely determine the structure function. If we then take this all into account and see if we take all the data for the different center of mass energies and show you here the uncertainty envelope of what we get from measuring the contribution in the region 10 to the minus 3 versus the unmeasured one. So basically, how well we can determine that, the quark contributions and the gluons and the orbital angular momentum, then you see if you measure really down to the full square root s, that you get a very well determined contribution of the quarks, the gluons, and the orbital angular momentum, and that the rest, which is kind of missing, is not so big anymore. So you have really nicely determined what the contribution of the quarks and the gluons to the spin of the proton is. So the next topic which we want to do is we really would like to image the quarks and the gluons inside the protons in 3D. So we want to understand what is their spatial location inside the proton. Are they sitting all in the core? Are they sitting at the rim of the proton? And then also what is their transverse momentum inside the proton? So you basically can kind of comprise this in what we call Wigner functions, which you can think about basically like a QCD genetic map of the quarks and the gluons inside the proton. So in one case, you can study the momentum space if you kind of integrate out the contribution in spatial, and then you get this nice 3D pictures where you see the transverse momentum as function of the longitudinal momentum. And you can see as you go to lower x that the transverse momentum distribution becomes wider and wider, at least at the current, is what the current models predict. You can do exactly the same in coordinate space. And what you see here is if you kind of integrate over the momentum space, that again, that the quark distribution, and here's that example is for the down quarks, grows. If you go down from high x to low x, what is also kind of what we know that the proton basically grows if you go from high to low X. So you can say, okay, nice to know this, but is this actually important for something? And particularly these 3D distributions of the proton are critical if you want to understand what has been seen as collective phenomena at the LHC, where you have in PP, PLED, and PP seen these really long-range correlations, which are very often go under the name of the rich in all of the systems. And if you want to understand this, basically in hydro calculations, which are done by Heike and Björn Schenke, then the biggest uncertainty at the moment in their calculations is actually how does the proton look like in 3D if it interacts with a gold nucleus or itself, and that you can kind of really understand very well how that works. And that the EIC can study this actually by looking to coherent and incoherent shape psi production in exclusive reactions. And I show you that in a minute how we do this. So what you use a golden channel, which is exclusive reactions like deeply virtual Compton scattering. So you have your electron, it emits a virtual photon, it scatters on a quark or a gluon. You emit a real photon, the quark basically comes back and you have a momentum transfer from the incoming to the outgoing proton. You then measure the cross-section here, and then you do a Fourier transform of this cross-section. And because PT and spatial location are, of course, Fourier transform variables, you get here then actually how precisely you can measure the spatial distribution of the quarks inside the proton. And you do this then as function of X and Q square, which you can see here. So that is as for different X for a fixed Q square. And you can, the models, for example, predict if you do that for a fixed X versus Q square, that as higher you go in Q square, as bigger actually the proton becomes, and vice versa. If you go down in X, the proton grows. The same thing you can do for shape psi, where you, because the shape psi directly acts the gluon distribution, and then you can get very nice distributions, how the gluons are actually distributed inside the proton as function of X. So at high X, they are more in the core, and at low X, according to the models, they would sit more and wider distributed inside the proton. So now we have understood the proton. Now we look into what is happening actually for nuclei. And one thing which we can do is we can precisely measure the proton distribution functions in nuclei. What you see here is the current knowledge of the gluon distribution with respect to the proton was from EPS 16. And we can use exactly like for the proton, we can measure the structure functions F2, which is sensitive to quarks and antiquarks. And if you take the derivative of the structure function versus Q square, you can access the gluon directly like in the proton, or you measure FL. Here you see actually a projection how well the EIC could measure the cross-section here, which is directly sensitive to F2 and FL. So very high precision over a wide range of X and Q square. And if you then project how well you can then kind of constrain the proton distribution functions, and you see here, for example, that is the gluon inside lead with compared to the proton, and the final results are basically the stashes. You really constrain the gluon nicely from very high X down to very low X compared to what we know now, which is in this dark gray band. I told already at the beginning, we really would like to understand non-linear effects in the proton and in nuclei. And in principle, you can think about the proton like a runaway popcorn machine, which generates gluons and gluons. And the gluon density actually really rises and rises as if you go to lower and lower energy. So the question is there a process which really tames this kind of nuclear gluons inside the nucleus? And there is actually, and this process is that you have gluon recombination, and this you can study by having a coherent interaction of your virtual photon on the gluon wall, which you have in a nucleus. And why we use a nucleus is because if you kind of want to reach this position in Q square where this kind of recombination happens, which is described by the saturation Q square here, then you can see that is it enhanced with a to the 1/3. So you reach this point much earlier than if you do that with proton, and that is more effective because you don't need so high energy colliders. So the golden measurement to do this is actually to look to dijets or dihadron production in EP and in EA, and measure their angular correlations as a function of your kinematics. And if you have actually a saturation, reached saturation, then what happens is that in the EA collisions, your dijet pair, your second jet gets actually kind of disappears because the correlation gets destroyed to the first jet because of the gluon wall. Here you see actually the coverage which EIC has from the models predicting going deep into the nonlinear regime in QCD for E gold. And what you can see is that the suppression of the secondary jet, really, if you go down in center of mass energy, becomes basically as big as a factor of 2. And we have actually lately done measurements for RIG where we see exactly this effect in PA. And also LHCb has measured very nicely that this exists. And here for EIC, we can really map out the X and Q square dependence of the saturation effects. Another really nice topic which we can do is we can map, like the proton, we can also map the gluon distribution in nuclei by measuring exclusive J-psi production. Again, the same process as in the proton. So you measure this here, you see for the J-psi, you see nicely the diffractive pattern, which comes from the form factor of the gold nucleus. And you see the incoherent part of the cross section, which comes that you scatter coherently on a proton, but not on the nucleus. And then if you take the coherent scattering and you do a Fourier transform, then you can, for example, very nicely reconstruct how the Wood-Saxon looks like for the nuclei if you kind of go at different X and Q square. And that is something which is very nice to know, particularly for heavy ion collisions. If you, in addition, take the incoherent one and measure this, you can actually kind of study how lumpy a nucleus is. So how the fluctuations and what the ratio of these fluctuations inside a nucleus is. So we have the physics, we have the accelerator, but what we also need is, of course, a detector. And all these different processes can be measured with 3 sub-processes: inclusive, semi-inclusive, and exclusive reactions, where the demands on the machine and the detector requirements become more and more difficult going from the left to the right, and the same for the luminosity. In one case, you look basically only on the scattered electron. Here you measure things in coincidence of the final state with the scattered electron. And in the exclusive reactions, you actually absolutely measure all particles which are produced in your interaction. So if I now span kind of a rapidity for the detector, so from rapidity 4 to -4, then actually if you look where your electrons are going, because they go very close to the outgoing electron beam or in the barrel of the detector, and the hadrons, which depend on high X or low X, span actually the entire region. So for inclusive reactions, what you need to cover is actually this side of the hemisphere. If you kind of then add the hadronic final state, you need actually a detector which has a barrel and has basically on both sides end caps which have to go very close to the beam. So we kind of want to measure as close as 2 degrees from the beam or even closer. And then for the exclusive reactions, in addition to the detector, what you need is detectors along the beamline, which measure actually this forward-going scattered protons or nuclei, so that you can measure this, the exclusive reactions. So the detector is a very compact, we envision a very compact detector which covers a large rapidity from -4 to 4. It needs very high precision, low mass tracking. It needs very good vertex resolution. And then it has gaseous detectors in the larger range. It needs electromagnetic hadronic calorimetry with equal coverage as the tracking, actually from -4 to 4. And then it needs very high performance particle ID detectors to separate pions, kaons, and protons over the same rapidity range, and also to give good electron-hadron separations, because we want really to identify on track level whether it's a pion, kaon, or a proton. And then we need large acceptance in the forward going direction along the beamline for all the auxiliary detectors, so that we can do very precise measurements of diffraction and detect the neutrons from nuclear breakup, because that is critical, particularly for the EA physics program. And then to control systematics, we need, of course, to measure luminosity and electron and hadron polarimetry. And all of this needs to be integrated in the interaction region. So we have actually engaged in a year-long yellow report activity in 2020, as we were all home due to COVID. We have a full concept of the detector, which is kind of getting worked out now. We have the technologies of the different detectors, depending on where they sit along rapidity for the tracking, electromagnetic and hadronic calorimetry, particularly the vertex detector is MAPS trackers. We think about the ITS3 kind of development for this. And then also hadron, lead powder, lead tungsten crystals, silicon glass development is scintillating glass development is something which we are doing. And of course, the PID detectors are based on Dirks and Rich detectors. We want from the beginning actually have a fully streaming data acquisition from the detector to disk. So we don't want to do any data reduction, which is possible because the DIS is a very clean process. So you have very manageable data rates of 500 kilohertz at the highest luminosity. So where do we stand with the project? So in January 2020, we received actually CD0 and the site was selected, which was Brookhaven National Lab. Just a couple of days ago, a week ago, we received actually CD1, which makes the project now a line item in the budget of the Congress. This year, we will continue to kind of further define all the design of the machine and the detector. And we have the goal for January 2023 to go for CD2 approval, which would baseline as a cost of the machine. And then CD3 would come basically more or less a year later, which is the start of construction. And we believe we will finish by 2031. Actually, it's the construction of all the machines. Right now, we engage in a process where we form collaborations and have called for detector proposals in March 21, and the proposals are due in December 2021. And we call for 2 detector proposals, and it is actually critical for the success of the facility that we have really strong collaborations and strong proposals for the detectors. We have worldwide a very active user group. We have at the moment 1,300 collaborators out of 34 countries all around the world. We would wish that there is more participation from South America actually to CEIC. And I hope that some of you hearing the talk kind of think about whether you would like to join us. Right now, we have 3 proto-collaborations forming. We have the ECIC consortium, and I give you here actually the links to this, which is based on a detector around the 1.5 Tesla solenoids. And you have Athena, which is also constructing a new magnet and wants to build the best detector possible for basically the EIC. And then we have a smaller activity which looks to a very compact detector. And also here you have also contacts for looking into the details for this. So in summary, it is true that we are so lucky that all the stars align. We have the series that we can actually ask the questions and really understand the visible matter. We have the detector technologies that we can actually kind of build a detector with the particle identification and the wide acceptance so that we can do the measurements which are needed. But most importantly, actually, the accelerator technology has made so much advances that we can build the EIC with high luminosity, polarization, cover a wide range of center of mass energy, have protons up to the heaviest nuclei, and can utilize actually a very demanding IR region with scrap cavities and a crossing angle involved. So that makes it different to now, where we see only the tip of the iceberg to understand the nucleon structures. That with the EIC, we can really see, hopefully, the full depth of the nucleon structure. And for the EIC science program, that actually means that we can understand the inner structure of the world around us. And the EIC is the only machine which will allow us this. And if we don't have it, we will not answer these questions. And I would like to invite everybody of you, let's get to work, build the EIC. We can definitely do it. And I hope you join us in doing so. Thank you.
Welcome, Elka. Very nice talk. Let's see if you have any questions. No, we still don't have any questions, but I have a curiosity. And when you talk about the possibility with the IC that can discover a new state of matter,
yeah.
Do you have any hint about this new state? What do you expect it to be?
So what you expect is that you really see basically that the gluons are so dense in the area which you have that you get recombination, which will lead to these decorrelations, as I showed, for example, from back-to-back jets or dihadrons, if you want to. It will lead to that, for example, diffractive measurements, because you scatter coherently on this wall of gluons which you have, gets enhanced compared to normal measurements on the proton, or if you're not in this kind of really dense gluon state. And there are some other effects which you will see. We have hints from Hera. We have a measurement from STAR, basically on this diejet correlations, which really follows very nicely the theory predictions. And the same is true for LHCb. They also have a very nice measurement which shows basically that these decorrelations of the diejets is happening. And there's nearly no other explanation for than that you scatter on this wall of gluons, which really kind of decorrelates and this back-to-back diejets.
Thank you.
You're very welcome.
Well, we don't have any other question. I'd like to thank you again for your nice
You're
talk.
very welcome.
Yeah, and just following the session, we have Jorge Molina. Molina, can you please share your slide? And Molina will talk about the amine detecting cone data using deep learning. Molina has his PhD in physics from the CBPF here in Brazil, worked with the FPG detector at the Zero. He got a postdoctoral fellowship at CMAT, and he also have a postdoc in CBPF and in the URG, the university that hosts this conference. Working for the CMS detector. Since 2009, he's a professor at the Faculdade de Engenharia da Universidade Nacional de Assunção, where he's working in the development of particle detection with neutrinos. Molina, please go ahead.
Okay, thank you very much for the kind introduction, Gilson. It's a pleasure for me to give a talk at the LISHEP. Now that I am not in Rio anymore, but always following what you are doing over there. And I will talk here about the data that we are taking over there not in Rio, but in Angra dos Reis, in a experiment called CONI, where CONI is Coherent Neutrino Nucleus Interaction Experiment. It's made by 6 countries and more than 30 researchers in these countries. So it's located at the Angra 2 power plant. You can see the dome over here, and nearby it's the container where the neutrino experiments are taking place. Not only CONI, but also Angra 2 experiment. So here we have the detector. I show here it's the outer shielding of polyethylene, 30 centimeters. Then we have 2 types of lead, one more pure than the other. And inside we still have the inner polyethylene, 30 centimeters as well. And inside that you can see the vessel where that it's at vacuum and where all the CCDs will go inside. So here we can see the box with in this case, we have 14 CCDs enabled for these runs of 2.5 years that I will show. So we can see here the CCDs that we use as a particle detectors. Normally, this kind of detectors is used in astronomy, in the focal plane of telescopes, but we don't want to measure photons here. We use much for particles. So these are the CCDs. It's very thick. It's thicker than the ones that it's been used at the cameras and normally. We can see the tracks of muons here. If there's a straight line, we can recognize that they are muons. When they have these shapes, this not so structured shape, we call it worms, that it's made by the electrons. And also we can distinguish very easily an alpha particle because it's a big spot with a lot of energy inside. And also we have this diffusion limited kit that it's when the energy of the particle recorded, it's very low and forms just a tiny point of light. So we can see here how we expect to catch a neutrino with the CCD. We have this low energy neutrino made at the reactors. So we are aiming it's measure the coherent neutrino that's never been measured at this energy. In 2017, the coherent experiment measured for the first time, but with a higher energy, more than 40 MeV. We have up to 11, 12 MeV neutrinos coming out from the reactor. So when they come, you can see from the left coming the neutrino, interexchange the Z boson, it's scatter the neutrino, and what it produces with the nucleus of the detector, in this case it's silicon, but the CCDs are made with silicon, depleted. So what we have is once that the nuclear recoils, it will strike the electrons that it's surrounding the other atom of the lattice. In this way, since we have an electric field over there, will make a migration of the electrons up to the top of the CCD, where there is a bucket where they will be kept. The electrons will be kept for until they are read by the electric fields in the reading process. Just one detail here. Well, since this is a P semiconductor, a P-type, so what will migrate are not the electrons, are the holes. So once they are inside, we can see that they can go to each pixel of that. It's pixelated, the information. So what we can see here is how it can be detected. So it depends mostly on the depth of the impact where it has been produced. So we can see if this is very near the top, it will migrate only inside the pixel, and we can see these kind of images. The electrons will distribute this one, and at the end, what we will observe is this just one pixel turning on. But then if we can go at the middle, for example, of the CCD of the thickness, it will start to migrate not only inside the pixel, but all around this central pixel, and will generate this kind of images where you can see a little bit more of pixels are being turning on. And also here, we can see from the bottom of the CCD how it will be at the end very spread out. These are effects that we know how to handle this. Mostly we can correct, and we can know from where it's coming due to these diffusion effects. So with the Connie images, what we have, it's, as I said, we have these 2K by 4K detectors that we put inside the box, and they have 15 micrometer square size each pixel, and what they will form an image this size, this kind, after 3 hours of exposure. We do it, there's a compromise in the exposure time, since what we have, it's we have a lot of particles, mostly background particles that are coming inside, but the processes of reading at low background, it takes like 30 minutes. So that's why it's a compromise to not to let too much time open, but also not so little time, because we will lose data if we read all the time. So inside this big image, we can see, for example, this is the kind of image that we are looking for in this case. We start with muons, which are the easiest drug to recognize. And for this is the size of this picture of this, we can see of this image of this object, it's 50 times 20 pixel, more or less. So what we did at the beginning, it was a muon selection analytically. It's a cut that we did. This is a very nasty thing, as you can see here. It's a lot of playing with the size, mostly on the length and the width of the image that we have to take into account and try to modulate that. So using this cut, what we can observe is that the fitting of this kind of extraction, it doesn't goes as the cosine square as we expect from a normal muon distribution in at the surface of the Earth. So that's why we are not confident with this kind of cuts. And also because, for example, we can take an image and we can pass all these analytical cuts. These are the events that pass the cuts. And we can see a worm here that, of course, that will contaminate the sample, the pure sample. And also, in all the muons and all the images that, all the objects that were taken out of the image will contain some muons that we could account that will not make a very good estimation of the number of muons. That's why we decided not to use this kind of analytical cuts, and we try to use artificial intelligence to take this, to analyze these images. And this has been done, for example, with the DECO experiment. It's a distributed electric cosmic ray observatory all around the world using your cell phone that you can register and use it as use the CCD of your camera as a detector. They will take out and will analyze these images with deep learning, with a deep learning process. So we use the same process that they did, since they can recognize drugs, worms, and spots exactly in the way that we do. But the difference is that we have more options that they did. So I can show here that we can recognize not only spot, muon, and worms, but we have also bad pixels. We have muon unsure depending on the penetration angle. And we have also undefined and segmentation errors. This is due, as I said, because it's open for 3 hours, the muons can go one on top of the other, and they can create these segmentation errors that the program won't recognize. So what we did is from these 7 million images took for 2.5 years by the Connie experiment from 2016 to 2018. And we have this dataset distribution where we could recognize mostly the muons. And then we have unsure muons, as I saw, these these numbers. This is a very unbalanced input for the deep learning method. So that what we have to do is try to equilibrate this one, and this you can be doing by data augmentation. It's called, where we already mentioned the size of the object and try and fill it by zeros when it's necessary to compress sometimes, and the other two to make bigger and try to get a better resolution. And what we can do is try to for the augmentation, it's to rotate the muons and also make some mirroring. Since we don't have any preferential incoming, it's isotropic, the incoming of the muons, and so we assume that. So we can augment the data sample. So, well, this is what I've said. For example, this is the original event, and we rescale to 32 by 32. Here we have 50 times 20. We get smaller to 32 by 32 and try to see which one fits best. After the augmentation, what we have is this final data set, which is much more equilibrated now, and we can put as an input for the deep learning method. And we did that with the deep learning model based on a very known method, VGT16. It's based because it's not the same, since we changed the input of the samples they did by 100 by 100 images. We use 64 by 64 in this case. So these have four layers of for extraction and 3 for classification of the objects. This is much more related with the deep learning process. So ones that we have, we can compare with, for example, with what is being extracted by the DECO experiment, which are these 4. We can achieve, for example, this for muons, 99%, 100% for spot in recognizing that. But even though it's very nice results, we prefer to keep this a bigger table because we have more inputs than they do, since we have undefined and we have bad pixels and error segmentation that we want to take into account. So that's why, even though we still have a little less accuracy in the muon detection, we have only, and I say only 94%, because over here we have 98, 99, and 97%. It's a little less, but it's workable, and we prefer to do with these results. And you can see here, for one image, for example, this is the one that I showed before. As an example, we have this image is of only one CCD. I say that we have 12 working, but all the results that I'm showing is for one, for the number 2, that it's the closest one to the copper box. And this is the run ID, and in this event, we can distinguish around 3,000 objects, that if you sum all these objects here. Using the deep learning algorithm, for this case only, we can detect 1,700 muons. All of these supposed to be muons, that if we can compare with the analytical cuts that I showed before, it gave the result 1,400. So we gain a little bit more of a statistic with the muon. But not only the amount of muon count, is that we are much confident that these are really muons, and we filter all the other particles as worms that I showed, that it can get dirty the data set, as in the case with the analytical cut. So also it recognizes the spot events. We can see here that it's really more spots than the other. And here we have the worms that it recognizes, and we filter all of these. So, and these are the residual events that it's compromised with bad pixels and the segmentation errors that I showed before. So at the end, we applied this deep learning methodology to the whole 7 million and more than a half number of images that we took along 2 years and a half. And we found that 56% of them were due to muons, which makes them the most abundant particle as the background, as it was expected, because it is, remember that we are at the surface level. We don't have any telescope of muon to filter these kind of things, because this CCD doesn't have the timing information. So we cannot apply the telescope for the muon tag and filter them. So it's a passive detector, so that's why we can only after we can reconstruct and make a cut after they've been recorded. So also we made the stability studies. As I said, we have 2 years and a half, but here we show only 2 periods of time. For example, from November to February of 16 and 17, which is represents the summertime here at the South Hemisphere. And also we can see that it's very stable, the amount of muons that were coming to this in this period. And also we have at the winter time, the median number are very close, although we can see that in winter time we have a little bit excess as expected due to temperature changes in the atmosphere, so making more, it's anti-correlated with the number of the production of muons. So for conclusions, we've been taking data for 2 years and a half, and for the first time, we used the deep learning method to count for backgrounds composed by muons, electrons, and alpha particles. And with this method of with deep learning, although was the very first attempt, we obtained better numbers than the analytical method, or at least for muons, recognizing the images. But we can improve that if we can recognize and separate, for example, the segmentation errors present. This is what we are in progress right now. The next step also will include the tracking of the muons, because as I said, I only present here the result of just one CCD we made for the other ones, but they behave almost exactly the same, so I didn't want to waste time. But what we can do is also make a tracker. It means that all the events that were generated in the first one pass through the second and then the third and all the inner CCDs. And this is what we are doing, and we are in progress about this. And the final aim is to make the recognition of the neutrino events from the low energy photon electron that makes this a very small amount of charge in the pixels. So, but this will require a different methodology than what we use here, because what we use here, we classify these events by eye and to make the training for the machine. Now, what we are going to use is the simulation of the neutrino events, and then see how it behaves inside the CCD, and from that, how the images are formed due to this scattering of the neutrino. This is in progress, but it will depend on the model of the neutrinos. Thank you very much for your.
Thank you, Molina. Nice talk also. Yeah, I don't see any questions, but I just have a curiosity, because you're using this machine learning to improve the resolution and the understanding of the muon. Do you have any problem with the diffusion, the identification? You have any progression with the machine learning, or you don't have any study with that?
No, we don't have problems, since what we can recognize, for example, in this kind of images. Let me see if I can get back here. In these images, you can see the diffusion in, for example, in these images, you can see the diffusion. This is at the bottom of the CCD, and this is at the top of the CCD. You can see that it's more diffuse over there than here. So it's already contained in in the sample that we put as an input to the deep learning algorithm. So it's included already there. So.
Okay, thank you. And just a little last question that Gilvan gave you congratulations for the talk and ask, are you aiming for the current elastic measurement?
Yes, we are aiming for that, but in these 2 years, we could not see any. What we do is we don't do it one by one. What we can do is let open for the reactor period on and off and compare if there's an excess when the reactor is on and it's off. After 2 years, we didn't see any difference for that, but what we need is more mass to achieve that, and we are doing an upgrade, but we are changing at the same time the electronics, so we can get better the performance of the noise reduction with these new skipper CCDs that we are testing. This week, we installed the new skipper CCDs that we will study, and then we will put in the container once that we are happy with that.
Okay, good news.
Okay, it's a new technology. That's why we are not so sure. We are in the commissioning process.
Oh yeah. Thanks again, Elena.
Okay.
For the
Thank
nice
you.
presentation.
Okay.
Now
I will stop sharing. Yeah.
Yeah, thank you. Now you move to Mauricio Martinelli. Please, if you can start sharing your slide, Mauricio.
Hello.
Hi. Mauricio, you'll talk about the new results in charm physics at LHCb. He earned his PhD at the University of Bari, Aldo Moro, and after that he got a postdoctoral position at NICEF, Lausanne, and at CERN. He worked for the LHCb experiment. Since 2009, he got a junior position at the University of the Milano Bicocca, if I'm correct. So please, can you share your slide? Yeah, that's yeah. Please go ahead.
Yeah, thank you very much for the very nice introduction. Let me enter full screen. Okay, can you confirm that you can still see the slides?
Yes, perfect.
Perfect. Okay, so I want to talk to you about new results in chunk physics at LHCb on behalf of the LHCb collaboration, of course. So, what is chunk physics at LHCb? Well, at LHCb, we usually separate chunk physics in 3 main areas that are mixing and CP evaluation, production and spectroscopy and amplitude analysis, and rare decays. And in this talk, I will cover just the first 2 of them. If you don't know the LHCb experiment, this is an experiment at the LHC. So we are designed to study proton-proton interactions at LHC, and it's designed as a spectrometer. So the interaction happens in this place where we have our vertex locator, and we record the flow of particles in this area of the detector. It was designed originally to study beam meson decays, but we soon noticed that it would work very well also for the study of chunk works. And this is also thanks to the very high production cross-section of chunk works at the LHC. It is about twice the production cross-section of big work decays. The efficiency of the detector has been optimal both in the PID and the tracking, and also we have very good time resolution and IP resolution. So without further ado, let's discuss how charm is produced at LHC. And at LHCb in particular, we have 2 main ways that we use to detect charm decays. One is so-called the prompt charm decays, in which the charm meson is directly produced in the proton-proton interaction, and the other one is the secondary charm production. In this case, the charm meson charm hadron is produced from the decay of a hadron decay. The 2 can be distincted by the different impact parameter of the charm hadron, but in one case it's very close to 0, and in the other case it's significantly larger than 0 due to the displacement that is introduced by the decay of the hadron. Oops, sorry. Another important thing about these 2 ways of producing charm at LHCb is that we can use in the case of the 0 mesons, we can use the soft ion produced by the decay of the D star into the zero pi to tag the flavor of the D0 meson, while in the secondary case, we can use the flavor of the muon produced by the B decay to tag the flavor of the D0. So let's start with mixing and CP violation and its experimental status. First of all, you can ask yourself why it's interesting to study mixing and CP violation in CHAM decays. Well, my answer to this question is that it's a unique place to search for mixing and CP violation, in particular for new physics couplings, and it's a discovery tool. Indeed, what the community agrees on is that CP variation in CHAM could probe extremely high beyond the standard model energy scales and is highly suppressed in the standard model. Indeed, the latest prediction are in the order of 10 to the minus 3, 10 to the minus 4, even 10 to the minus 5. This is also complementary to direct searches for beyond the standard model particles, and at LHCb we have billions of decays needed to be studied. In this plot, I just wanted to show the reach of indirect searches for in physics in some specific couplings. And I wanted to remark that the reach of CHAM, or also kaon or dihedron decays is much larger than the reach of direct searches that we can perform at LHC or at future colliders. On the other side, though, we have to admit that the predictions are challenging in CHAM, therefore we cannot use it as a precision probe, but nevertheless it's an interesting laboratory for non-perturbative QCD and exotic carbon dynamics. And nowadays I believe that it's fair to say that we are living exciting times for CHAM physics, because in 2019 we observed for the first time the CP violation in CHAM decays. And today, we observe for the first time the zero eigenstates mass difference. To understand what these results means, I just wanted to briefly introduce neutral meson mixing, or remind yourself about neutral meson mixing. It is the quantum mechanic effect for which when you have to flavor eigenstates D0 and D0 bar, that they can mix, they can be combined to produce two mass eigenstates, D1 and D2. And in the case that the mass difference between these two eigenstates, or the width difference between these two eigenstates is different from zero, what you will observe is that in the evolution of time, the D0 will turn into D0 bar or vice versa. And so it's important to study the evolution of time of the D0 bar decays and measure the mixing parameters X and Y to measure this effect. And another thing is that mix is important also for studying of indirect CP asymmetry, because we can have, for example, this scenario in which there is an interference between mixing and decay, in which we have a D0 decay to a specific flavor eigenstate F, but maybe this decay can happen also through the mixing to a D0 bar decay that decays to the same final state. And the difference in the weak phase between these two amplitudes is phi F. In case there is a difference in this weak phase, this difference is exactly opposite in the case of the D0 bar decays, and therefore we have a difference in these two amplitudes. And this difference in these two amplitudes brings us to CP violation. And to study the CP violation effect, we need to measure the asymmetry, but the asymmetry is dependent also on the mixing parameters, not only the weak phase parameter. So that's also why it's important to have a precise determination of these mixing parameters. In LHCb, the most recent measurement of this parameter, and the one that we use to determine for the first time the difference in mass between the two D0 eigenstates, is that the one of the golden channel D0 to be short by pi. We have about 31 million decays that we detected at LHCb, and you can see a nice distribution in the Dalitz plot of these decays. And the interesting part of this decay mode is that it allows us to measure directly CP X and Y, and also CPV from the measurement of Q and P. In the past, the most used approach was a time-dependent amplitude analysis, but this approach has a lot of challenges. Therefore, we decided to attempt a new approach. It is called LISHEP, that we started in 2019 and first applied to LHCb data also that year. And the idea of this Winfried method is to extend the Bronstein mixing measurement concept to multi-body decay. So this Bronstein mixing measurement was the way that mixing was first observed in channel decays and D0 to K5 decays. So the idea is that we can study the decays of the D0 candidate to a K-star plus pi minus decay, and this is double Capillo suppressed decay, and its interference with the other pattern in which the D0 first mixes to the D0 bar and then performs a Capillo favor decay to the same final state. If you look at the Dulles plot, the K-star plus pi minus decays are in this area of the Dulles plot that we call Bronstein, while the K-star minus pi plus are in this area that we call the right side. These are the Capillo favor decays. So what happens is that with mixing, at the variation of the evolution of decay time of the D0, what happens is that some events move from this area of the Dulles plot to this area of the Dulles plot. And we decided, therefore, to study the ratio in decay time of events in this area of the Dulles plot with respect to the events in this area of the Dulles plot. This ratio can be studied with this formula here, can be approximated to this formula here, and you can see that this formula depends on some hadronic parameters that we can determine, like RP, this is the ratio at decay time equal 0, but also the CB and SB parameters apart from the X and Y parameters. The CB and SB parameters are dependent on the strong phases of the decay, because in different areas of the Dulles plot there are some different strong phase variations between these points in K short pi plus and K short pi minus. So what we decided to do is bin the Dulles plot in 8 regions of approximately same strong phase difference, and measure these hadronic parameters CBS and the SB from quantum correlated D0 to 0 bar pairs using external input from Clio and ST experiments. So what we observe is that by applying this approach, we can we can find the mixing in each of these beams with a slightly degraded precision with respect to amplitude analysis, but at the advantage of a significantly simplified analysis. This is what we did with the run-2 data set. On the left, you see the results on the mixing. So when we combine together the D0 and D0 bar decays, and you can see that the mixing aspect is clear. In the red, you have the no mixing, what we would have had with no mixing. And also, this is reflected also on the contour that you see on this plot, where the XCP parameter is significantly different from 0 by more than 5 sigma. So this plot is just showing the ratio in each of the phase space beams R1 to R8 that we studied in decay time. To study CP violation instead, we subtracted this ratio in each of these phase space beams in decay time for D0 and D0 bar. So we measured those two ratios separately and we subtracted them. And as you can see, we have no sign of CP, apparent sign of CP violation, and this is also reflected in the contour plot that you see here on the left. And of course, in the result of this delta X and delta Y parameters. Regarding systematic uncertainties, the largest ones are from trigger-induced efficiency correlations and from the broad measurement of decay time from secondary channel from behaviors. Also, we observed some small detection asymmetry facts that are mostly relevant for the CP violation measurement. One thing to remark in this table is that the strong phase input, that is something external from our experiment, also plays a large role in the measurement of mixing. So in case we wanted to reduce even more the total uncertainty at a certain point, not only by adding data, but we will also need to reduce these effects. So we will also need some help from our colleagues at ST, for example. Another measurement of CP violation that is very recent, you can find in the archive, is the measurement of time-dependent CP violation D0 to HH decays. This is CP violation into body final states that can be described by a final state dependent constant term plus a term that depends on the evolution of time that we decided to call delta Y and was previously called as A gamma. As you can see, this term is also dependent on the mixing parameter. That's why it's important to determine them with very good precision. Standard model expectations for this delta gamma are in the order of 10 to the minus 5 from these two papers. At the LISHEP, we studied the run-2 data set from 2015 to 2018, 6 inverse femtobarn, about 18 million D0 to pi pi, 58 million D0 to kk, that are the Cabibbo-suppressed decays that we want to study to search for CP relation, and 519 million of Cabibbo-favored D0 to k minus Laplace decays. In these decays, we do not expect any CP relation, and we use them as a control sample to test our analysis technique. So let's start from the control sample. You can see that indeed our analysis technique is working because we do not observe any CP relation effect. And once applying the same correction that we had to apply to the control sample to our Cabibbo suppressed samples of the 0 to kk and the 0 to pi pi, we see some trend, but of course we do not see any CP relation effect because also the combination is still consistent with 0. But what I really would like to remark is that we have a precision of 10 to the minus 4 already with LHCb, but the systematic uncertainties that we achieved with this analysis approach to the form are extremely low, in the order of 10 to the minus 5. So this makes this analysis very promising for the upgrade of the LHCb that will happen starting from next year. Finally, I wanted to report some of the latest results in spectroscopy. It is interesting to study barium spectroscopy and Chern barriers in particular because LHCb allow us to measure some of the properties with unprecedented precision, particularly lifetime and mass, but also it allows us to test some hypotheses like the quark picture in different scenarios. In this, for example, in this quark picture, it is believed that the Avis quark is static and spinless in the limit of its mass being much larger than the mass of the other two quarks, and therefore it's believed that these other two quarks, the system can be described as a static quark and the other two quarks orbiting around it. And this, of course, creates different excitation patterns that we want to test at the LHCb with our measurements. But let's start from the lifetime of the omega C baryon. This is particularly interesting because until 2018, the most accepted lifetime hierarchy of Chern baryons was this one, in which the omega C baryon was the one with the lowest lifetime. But then we perform at LHCb the most precise measurement of omega C and the XIC lifetimes that subverted this scenario using baryons from the various decays. And what we noted is that the omega C baryon lifetime was larger than the lambda C baryon one. But of course, since the result was some kind of controversial, it was necessary to cross-check the result with an independent sample. Therefore, we analyzed run-2 data of promptly produced Chern baryons on XIC decaying to pkk pi and omega C to the same final state, and the D0 to kk pi pi as a control sample. We decided to perform the measurement by studying together both the invariant mass of the baryons and this variable that is called log IP chi-square that is used to study the separation of the Chern baryon from the primary vertex, so the displacement of the Chern baryon from the primary vertex. And you can see that this is necessary to be studied because this is the variable with which we can separate the prompt decays in red from the secondary decays in green that will not be absolutely separate in the invariant mass plot. Once we've been in decay time and we include acceptance effects, we can measure the lifetime of the omega C, PPK to pkk pi, and the XIC to the same final state in these two plots. And once again, we observe that the omega C was larger than lambda C, and omega C lifetime was larger than the lambda C1 and the XIC1. So we confirm this hierarchy that was originally determined by ourselves in TT with a different sample. Finally, I wanted to report on the excited omega C baryons. This is because in 2017, we first reported 5 strikingly narrow structures in M omega C, MXICK plus mass invariant mass distribution. And those were considered as omega C excitations and a natural spin structure of 1 alpha and half, 2 half, 3 half, 5 half for each of these 5 final states. 5 resonances was proposed. Unfortunately, the spin structure cannot be studied in promptly produced decay, but we needed exclusive decays of omega B to XIC plus K minus pi minus to determine the spin structure of the decay. You can see this omega B invariant mass in this plot. We have a very nice signal that we selected to the states. So this is the analogous of this plot, but made from omega B decays. And what we observe is that there is, first of all, a state that is probably missing. Therefore, this is be reinterpreted. It's probably not an omega C excitations. And but at least we can see 4 out of the 5 states that were previously observed. And one other thing that that also need to be understood is maybe there is a state at threshold here, since we do not see the same background that was seen in the prompt analysis. But having this very nice peak and very clean peaks, we can perform an angular analysis studying the Licity angle between the K- and the P- in excess series frame. And what we observed by studying the angular distributions using this formula and comparing with the results from our fits is that the spin 1/2 hypothesis was rejected with slightly more than 2 sigma for the omega C 3050 and with slightly more than 3.6 sigma for the omega C 3065. So this probably indicates that we need a bit to revisit the spin assignments. Maybe a potential alternative spin assignment would be 1/2, 1/2, 3/2, 3/2, 5/2 in case there is a state here at threshold. So, but we need, of course, more data to understand it better, this picture. So to conclude, I hope that I convinced you that CHARM is a very active field, providing a lot of new and interesting results at LHCb. And we already produced some historical results in the field of mixing and CP violation, and we are deepening our understanding of QCD. For the future, next year, we will start taking data with the LHCb upgrade that we record about 15 less femto, about 5 times the current data set by 2030. And of course, we are working to prepare our new detector and push forward our limits. Thank you for your attention. That's all.
Thank you, Mauricio, for this nice set of results that you bring from LHCb, and very productive for me. And let's see if you have a question for the audience. If not, just a curiosity, last about the excited omega, they missed the state that you claim it should be from the lack of statistics, or do you expect to see something better with more data in the 1/3?
Okay, yes, at this moment, we cannot say yet whether this is lack of statistics, because you can see there are very few events in this plot, or it's indeed really missing. So in here, yes, we need definitely more data, both to understand the structure of threshold and whether this state is an omega C excitation that, in case we will record more data, for example, in I3, we will probably see, or it's another resonance from another state. Yeah.
Okay, thank you.
But definitely, the way to understand, to have the best picture is to study exclusive decays, because there you really have a complete spin structure that you can find.
Okay. Thank you again for your talk, and congratulations. We move to the next one, which will be given by the David Fazzini.
Yes, can you hear me?
Yes, perfect. You can share your slide also.
Yeah, sure.
Please. Yeah.
Yeah, also.
Okay.
Let me turn on the camera.
David will talk to us about the CP violation, the abuse sector at the LHCb. He got his PhD at the University of Milan Bicocca, worked for the LHCb experiment, and now he's a research fellow at the same university. Please go ahead.
Yeah, thank you. So yeah, today we'll give you a short overview on the latest CP violation results performed at LHCb. I will start with a short introduction, and then I will go directly through the LCD results. I will talk about the latest one related to the CKM gamma angle, then something on the delta MS mass difference, and then I will move to the CP violation in two-body neutral BDKs and imbalance, and then I will go to the conclusion. So the CKM metrics describe the quark charged current weak interaction. You can find a representation of these metrics here in the slide, where there are these three phase terms that are the one related to the CP variation. So the CKM matrix is very important since it's a key test for all the standard model, and in particular the test of its unitarity is important, but we can also go to measure the different magnitude by means of branching fraction and missing frequencies, or measure directly the phases in the CP violation. And of course, all these quantities are sensible to effect from physics beyond the standard model. So from the consistency of the various measures, we can have a good view of what happens. And here on the bottom, you can see the usual triangle with the unitary constraints, and the triangle with all the measures performed to determine the various angle and the edges of the triangle with all the measures. And so in the moment, this is very constrained, various results from a different experiment. So starting, I will start talking about the CKM angle. Gamma is a phase between the B2C and B2U transition, can be determined already at 3 levels, so it's an important standard model benchmark. And at the moment, we are two different measurements, one performed directly and one on indirect measurement. And there is a gap between these two that is going to be is closing. And so, as I said, it can be determined by 3 levels, but also by means of measurement of the B plus to DK plus DK mode, for example, which I will talk in a minute, looking at the D meson decaying in 2 and 3 bodies. But we can also extract a measurement of gamma from the time-dependent CP violation in BS to DS K by pi, and in the loop measurement of the BS to K, the KK. So starting from the B plus to DK plus mode, using the D meson decaying into body, LISHEP performed a measurement using both run 1 and run 2 data, so up to 9 inverse phantom. And in this measurement, we are performing a simultaneous measurement of all the CP, many CP observable, measuring on both fully reconstructed decays and 19 partial reconstructed decays. So the key point in this case is that starting from the B, we can reach these two final states, one with the D0 and one with the D0 bar. And in one of the two cases, we have this contribution from gamma that should change the amplitude of the decay. And so we are going to measure different decay rates, plotted here in the slide, and also the CP asymmetry, which in both of these cases, there is this gamma element which appear. And so from this measurement, we can extract some information on this angle. And here you can see the invariant mass distribution in the K pi K spectrum for the two different decay processes. On the left for the one with the D0 and the right with the D0 bar. And as you can see, there is a significant difference in the peak height, both in the full reconstructed decays, which is the white peak, and also in the partial reconstructed decays, which are the two peaks in blue, which are very different in the shoe plot. And from this difference, if we want some more quantitative results, we can extract CP asymmetry equal to 45% for the full reconstructed decay and 71% for the partial reconstructed decay. But before moving to show you the results of gamma, I have to talk also of the other measurement performed on the same decay mode, but with the D, which decays in 3 body. So this is another analysis performed always at LISHEP using the full run 1 plus run 2 data sample. In this case, we are going to measure the CP variation parameter, that means on the invariant mass fit in Dalitz plot bins. So the bins are the one reported here on the plot on the right, while on the left you can see the mass distribution for all the decay mode that enters in this analysis. We have some external input we are taken from Cleo and BEST3 regarding the strong phase, but at the end, this turned out to be the most precise gamma measurement performed from a single analysis. And the results are here on the right. So we have measured a gamma equal to 68.7 plus or minus 5 degrees. And of course, we have also results for the other observable So if you are going to combine these results with the results obtained from the previous analysis that I talked before, you can obtain the plot reported in the bottom. So the red regions are the confidence, the contour regions obtained for the decay into body. And as you can see, there is an ambiguity on the results, but this ambiguity can be solved when adding these results on the 3K pi and allowing a better estimation of the gamma parameters. Moving to another analysis. In this case, gamma is extracted from the time-dependent measurement of the SK pi decay. Again, if you use the full run1 plus run2 data sample, and in this case, we exploit the CP violation due to the interference between mixing and decay to extract some information on gamma. We have many contributions in this, so we have from different channels. So this is indeed an amplitude analysis, and is performed following two different strategies. One model dependent, and the other describing basically each resonant with an amplitude model, and then performing with a model independent fit integrating over the whole phase space. And so here on the left, you can see the mass distribution in the ds-KK in the K pi spectrum. And on the right, instead, you can see the same plot background subtracted with the different resonances contribution. And in blue, in blue, you can see the total fit overlay. So from these two kind of approach, we can estimate, we extract the value of gamma, and which are reported here in the slide, and both of them are in very good agreement one to each other. And here on the plot, you can see the decay time distribution that is being fit. It can be used to extract this value. With the blue is the fit. In red, instead, there is the decay time acceptance. While on the right, you can see the oscillation asymmetry and of the two decay mode, and where the shift between the two is indeed due to the CP violation. So there are a lot of measurements. There are many measurements on gamma, so performed recently. So we can evaluate also a LSCB average of this quantity. So the previous measurement was reported here in this conf note in 2018. It was 74 plus 5 minus 6 degree. And now the new average from LSCB, which include all the analysis that I talked about today and other most that are reported here in this other conf note, is 67 plus or minus 4 degree. And here on the bottom, you can see the contour plot on the left for the 2D plot gamma versus RDK. In green, there is the full LSCB combination with the two regions at 68 and 95% of confidence level, while there are also other regions related to specific decay modes. On the right, instead, you can see which is the contribution of the different B meson in the determination of gamma. As you can see, the B plus is the most one giving more precise results. So just to complete this overview on the gamma measurement, so LSB is closing the sensitivity gap between the direct measurement and the global fits that I mentioned before. Here you can see in the plot the different values for the LSCB average and the CKM AUT fit. And so indeed the discrepancy is start getting quite small. And of course, we expect more precise results in the future thanks to the new measurement of delta MS and beta S that are vitals for both the CKM fit and measurement that we'll talk to you in a while. But of course, any disagreement between these direct measurement and global fit would mean effect from physics beyond the standard model that came up with new particle mediators in exchange loop. So really stay tuned for the next update. And so regarding the measurement of delta MS, LISHEP performed two different analyses on the BS2DS pi and the BS2DS 3pi decays. So that you can see here on the right the invariant mass distribution for these two decay modes. For the BS2DS pi, LISHEP using only the full run 2 statistics equal to 6 inverse femtoman, since there was already published analysis using the first part of run 1. And in the total, we have 380,000 events. While for the BS2DS in 3pi, we use the full run 1 plus run 2 statistics, with 150,000 events. So delta MS is extracted from a background, from a fit to the background subtracted decay time distribution. And as you can see from the plots, we obtained a spectacular decay time asymmetry distribution where the oscillation between the two mesons is clearly visible. And here on the bottom, there is a table with the results obtained in this analysis. So the first row is related to the analysis on the first run 1 sample for the BS2DS pi, and then we have the two results that I mentioned in this that I show in this talk. And in particular, I want to highlight the measurement, the results on the BS2DS pi, which is very precise, even more than the world average at the moment. And in here is the LISHEP combination, where it is performed using the 3 analyses mentioned before, plus other 2 using GEPSI to KK decays. And of course, this measurement is interesting on its own, but is, as I said before, a crucial input for the future update on the CP analysis and the global fit. So it's very useful that we are able to reach this kind of precision. So moving to the second part of the talk, this is the CP violation in 2 body metal B-meson decays. And so in this analysis, we perform an ambient likelihood fit to the invariant mass, decay time, hemispheric probability for 3 different final states, K pi, pi pi, and KK. And we are going to measure the time integrated CP asymmetry and the time independent CP in B2K pi and BS2pi and the time dependent CP asymmetry in B2pi pi and BS2KK. And in this second case, we are going to measure these 3 parameters, C, S, and A delta gamma, which are related to the direct CP violation, the mixing induced CP violation, and the symmetry rising for the different in lifetime. So it's performed using 2 different strategies, using the first part of the run 2 dataset. So we will have an update in the next years. The results obtained with the 2 methods are perfectly consistent in agreement with the previous results and represent the most precise result obtained from a single experiment, and are listed in the table on the left, while on the right you can see all the fixed parameters that were considered in the analysis. Here you can see 2 plots. So we have the invariant mass distribution for the pi pi and the KK spectra, and the asymmetry plot for these 2 final states using 2 different kind of tagging algorithm, where in both cases the oscillation is clearly visible. And then, of course, these results allow to have a sensitivity to the alpha, beta, gamma, and beta S parameters. And in this case, for the KK mixing parameters, we obtain a difference from the no CP violation hypothesis higher than 6 standard deviation. And so this represents the first observation of time-dependent CP violation in beta-best decays. And here on the plot, you can see the results in the 2 plane C pi pi and SPI pi and CKK, SKK for the various experiments, Rebel, Babar, and LISHEP, and also with the 2 analysis, 2 strategies followed for this analysis. So from the results from the B to K pi, if we combine this with the direct CP violation performed in B0 to K pi, pi 0 decays, we can have some hint of the isospin symmetry or asymmetry. So this is the first analysis with only 1 track decay at the Hadron Collider, and we expect isospin symmetry, but as can you see from these slides, in particular from the results of the CP performed in the 2 decay mode. This difference is far from 0 by more than 8 sigma. So this is indeed an hint of the isospin symmetry breaking. As it is clearly visible looking at also the plot for the two final states, which are very different between B0 and B0 and B0 and B0 and B plus. So first things that I want to show you is the CP violation in baryons decays. This is like the decay in a proton KK final state using the run 1 and the first part of run 2. In this case, we are going to measure the CP asymmetry determined at described in the slide. And for the moment, the results are all consistent with 0, but we expect significant improvement in the run 3. And so here, there you can see the results for the different resonances, and here in the plot in various mass distribution for the P2KK final state with the fit overlay. And also here you can see the fit results in different mass region for the different resonances. So just going to the conclusion, so the CB produced outstanding results in the CP on the CP evaluation and mixing in the beauty sector. We perform different measurements of gamma and delta MS, and we also have the first observation of time-dependent CP evaluation in vis-a-vis sector, and we are still deepening the K-pi puzzle. But these are just an appetizer. We expect to have more significant and excited results in the near future with the LSC and the LCB coming upgrade area, and so stay tuned. So thank you for the attention.
Okay, thank you, David. Any question? If not, I have a curiosity because just in the beginning of the talk, you showed the gamma angle measurement in direct and indirect measurements. And after, when you show the result from the old result of LHCb and the new one, you have a similarity in the numbers. Do you have the old one was doing analysis, indirect analysis, and the new one direct, something like that, or you don't have any kind of combination of this?
No, yes, as you said, this is just with previous results with H plus 20, but we didn't count all the new LCB results. So
okay, it's not a difference in the technique of the analysis. No.
Yeah.
Okay. Okay, then thanks again, David, for the presentation. And we can move to the other presentation from the Julian Castro. Are you there?
Yes. Hello.
Good. Can you please share your slide?
Yeah.
Thank you. Okay, Julian will talk about the lepton flavor university at LHCb also. He's a PhD student at Galego Institute de Física de Altas Energias in Santiago de Compostela, and his current research is on the testing of lepton flavor universally with semi-leptonic B-quark decays at LHCb. Please go ahead.
Okay, can you confirm that you see the slides and everything?
Yes, perfect.
Okay. So hello everyone. Thank you for having me. Well, I will start explaining what is lepton flavor universality. So lepton flavor universality is a property of the standard model where the couplings of gauge bosons and leptons are the same independently of the lepton flavor. So this means that the branching fractions of decays that go into leptons would be completely independent on the flavor of the lepton and would only depend on other properties of the leptons, like their different masses, for example. So in the past decade, there have been some tensions between experimental results and standard model predictions in B-quark decays. So these tensions are important because if a violation of this principle were found, it would be a clear sign of new physics. It would probably imply the existence of new particles outside the standard model mediating these decays. Like some theories are Char-Higgs bosons, leptoquarks, and many others, for example. So the first thing I will talk about are neutral currents, which are decays of the type B2S and 2 leptons. In the standard model, these kind of decays are strongly suppressed since they do not happen at tree level. This also means that these decays are very sensitive to contributions from new particles outside the standard model that could be mediating them. So they are a great probe for this kind of analysis. So to measure this at LHCb, what we do is measure a ratio of branching fractions like this that you can see in this formula in a given Q-square region. We do it this way because we can achieve a large cancellation of theoretical uncertainties when computing this ratio. And the Q-square region that we use is usually just below the J-side resonance that you can see here in the right side plot. And the theoretical prediction for these ratios in that region is around unity. Then we have some resonances in this spectrum from J-psi and psi, for example, as you can see here, which are used as control regions in the analysis that I will talk about. One big difficulty that this analysis have at LHCb is due to the differences in the detection of electrons and muons in our experiment. Electrons have a lower trigger efficiency at LHCb, and they also lose a large amount of energy through brainstorm radiation. This last effect is partially countered by using photons which are detected at the electromagnetic calorimeter and using them to partially reconstruct the initial momentum of the electrons. To reduce the systematics due to these difficulties, this ratio is actually measured as a double ratio by using the J-side resonant modes, which you can see here, as a normalization for the non-resonant modes. And this is possible since the J-side to 2 leptons decays are measured to be lepton universal with a high precision. So the first measurement I will talk about is RK star, which was done with round 1 data. The signal mode in this analysis is a B meson going to a K star and 2 leptons, and this was done with 2 different Q-square beams. You can see these beams represented here in the plots on the bottom, where you have the invariant mass of the final state particles in the x-axis and the Q-square in the y-axis. So here on the left, you have the muonic sample, and on the right, the electronic sample. And because of what I said before, you can see clearly here that the electronic sample has very broad resonances compared to the muonic sample. And also we have bigger radiative tails, which are these diagonal things here. And even some of that resonance even penetrates in the central Q-square beam, as you can see here. So in order to extract the yields for the signal modes in this analysis, fits are done for each Q-square beam and for each lepton type. These fits are simultaneous in the resonant and in the non-resonant modes, and you can see the results here in these figures. You can see on the left the results for the 2 Q-square beams, and on the right for the resonant mode. And the plots on the top correspond to the muonic modes, and the plots on the bottom correspond to the electronic modes. As said before, you can see how the resolution in the electrons is worse. We have broader peaks, and also on the central plot, you can see this gray component, which is the J-side resonance that I talked about earlier, which is contaminating this sample. So with the yields extracted from these fits, the ratio of branching fractions RK star can be computed. And for this analysis, the results were just a bit more than 2 sigmas below the standard model predictions. You can see the results in these plots compared with the standard model predictions in the left and with other measurements by Babar and by Bell on the right. So another important measurement that was just published this year is RK. This is an important measurement because it was done already with the full LHCb data sample with both round 1 and round 2. The analysis is very similar to the previous one, to RK star, but here the main differences are that we are using only one Q-square range. The selection process is a bit different, and then the fit strategy is different in that here we are fitting first the resonant modes, and then those fits are used to constrain the other fits to the non-resonant modes. These fits are also simultaneous, and here RK is directly put as a parameter in the fit, so its value is directly extracted from the fit. You can see the results of the fits here on the left, with the electronic mode in the left and the muonic mode on the right. You can see again the worst resolution of the electrons. And well, the result of this analysis was 3.1 sigmas below the standard model prediction. This result is compatible with the previous measurements by LHCb, which were done with fewer data. And this is the most precise RK measurement that we have today. You can see it on the right, this LHCb result compared by the results of the same value by Bell and by Babar. So the next section is about charged currents, which are semi-electronic decays of the type B2C, a lepton and a neutrino. This kind of decays do happen at tree level and are mediated by a W boson. So these are more frequent than the previous decays of the type B2S. Because of this, we can measure them at LHCb by using the ratio between the tauonic mode and the muonic mode. And since we are using the tauonic mode, we need to select a decay mode for the tau. The two most common choices are the muonic channel, which is the tau going to a muon and two neutrinos. This has the advantage that here, when computing the ratio, we have the same final state particles, both in the top and in the bottom of the fraction. So there are systematic uncertainties that cancel. But this mode has the disadvantage of having a huge presence from inclusive muonic decays. On the other hand, we have the hadronic channel, which is a tau decaying into 3 charged pions and a neutrino, which has a lower branching fraction, but it has the advantages of only having 1 neutrino in the final state, which helps with momentum reconstruction. And also, since we have 3 charge tracks from the pions, we can reconstruct the tau decay vertex. Having that decay vertex will help also with momentum reconstruction and also with background suppression, as we will see later. So the first analysis of this kind of decays that I will talk about is RD star in the muonic mode. As said earlier, here we have the same final state particles both in the tauonic mode and in the muonic mode. So these both channels are selected, and then they are disentangled using a multidimensional fit, which uses the energy of the muon, the missing mass, and the Q square. You can see the results of this fit here on the right, where we have the tauonic mode on red, and we have the muonic mode in dark blue. So just by extracting the yields from this fit and by using efficiencies from the Monte Carlos, the value of RD star can be computed. And the result for this analysis with round 1 data was 2.1 sigmas above the standard model prediction. Another important measurement was RJSI. This one is, again, very similar to RD star, which is the previous one. The main difference here is that we have a charm B meson instead of a regular B. And charm B mesons have a lower decay time than the other B mesons, about 3 times less. So in this analysis, they take advantage of that by using the V decay time as a dimension in the fit, along with the other 3 variables. So you can see the results of the fit in this analysis here on the left. Again, the red component is the tauonic channel, and here we have the muonic channel on dark green. And with the jits from this fit, the result for RGSI is computed, again with round 1 data, and this was within 2 sigmas about the standard model prediction. So finally, we have RD star in the hadronic mode. This analysis is different from the previous one, since here we have the tau decaying to 3 pions. So here we are not measuring the muonic mode, and instead we measure a different normalization mode, which is the V meson decaying into a D star and 3 pions. This is chosen because that way we have the same final state particles in both sides of the fraction, and this allows to cancel some systematic uncertainties. And then once we have this ratio between the signal and the normalization mode, we can use well-measured branching fractions as external inputs that are displayed here to compute the final result of RD star. Here, as said earlier, we have only 1 neutrino in the final state, which will allow us to improve the momentum reconstruction of the tau and of the V meson. And since we have also the tau decay vertex, we can use the flight distance between the V and the tau vertices in order to select the signal, since we can make a cut in its distance. So this will suppress a lot of background, and this also can be used to select the normalization mode, since the 3 pions are coming directly from the V vertex. So the signal yield here is obtained from a fit in 3 dimensions, which are the Q square, the decay time, and the output of a boost decision tree. This VDT is especially important since it is used mainly to suppress background from double charm decays. These are the most common source of background in this analysis, since they have practically the same topology as the signal, but with a charm meson instead of a tau. And then the normalization mode yield is obtained by fitting the invariant mass of the D star 3 pi system. You can see the results of these fits here. On the right, you have the fit around the V mass, which is the normalization mode. And on the left, you have the 3-dimensional fit of the tauonic signal, which is represented in red. And here you can also see that most of the background is from double charm backgrounds, which are these V2, DT, and more things. So from the results of these fits, and with the formulas that I showed earlier, RD star was measured to be 1.1 sigmas higher than the standard model prediction. So what's interesting about these measurements is that if we combine the results of RD star by LHCb with the simultaneous measurements of RD and RD star that Babar and Bell did, we can look at the global average of all these measurements, and we can see that it is currently sitting at 3.1 sigmas from the standard model predictions. So for the future, as you have seen, most of the analysis that I talked about were done just with round 1 data at the moment. So when round 2 data is added to that, as they did with the RK analysis, for example, round 1 plus round 2 has around 4 times as many statistics as just round 1. So we can expect a significant reduction of uncertainties just from that. And then in the future, when we have also the round 3 data, in the V2C decays, we expect systematic uncertainties to dominate over the statistical uncertainties. In the V2S decays is more difficult since they are more rare. So the uncertainties that we can obtain here are dependent on how well we can improve those systematics. You can see here on the right some plots which show projections of what we expect those uncertainties to be depending on how well we improve the systematics. So apart from updating the current results that we have with Ranchu data, LHCb is also working on simultaneous measurements of RD0 and RD star, both with muonic and hadronic tau decays. Also the same, but with RD plus and RD star. And LHCb is also working on new ratios like R5, R lambda, and many others. So to conclude, we have seen some intriguing tensions with the standard model in ratios of branching fractions in big quark decays. There might be potential for new physics, but we need smaller uncertainties, and LHCb is working on updating the current results that we have with the Ranchu data to provide those smaller uncertainties, and we are also working on measuring new ratios that will hopefully shed some light in these anomalies that we have seen. So stay tuned and thank you.
Okay, thank you for your talk, Julian. Yeah, very interesting this last result that you show, and this possibility to do new physics. It's very interesting.
Thanks.
So you have any question?
Slide 9.
Yeah.
Okay, the LHCb measurement for RK is the most precise, but it is far from one. How this difference can be explained? Okay, yes, so yes, these differences, well, these depend on the theoretical models that we have. Well, I don't know a lot about these theoretical models since I'm an experimental physicist, but my understanding is that we have some models like the ones I talked about earlier, like the Charge-Higgs boson of the leptoquarks, that could be new particles that are mediating this kind of decays and changing the value from 1, which is what we expect for this. These new particles would couple different to different kind of leptons, so they would change this kind of ratios.
Okay, thank you. That was, I just have that question also, but when you said in the summary that you have a range for new physics, and I just skipped that, but yeah, I understand your point. Okay.
Just, I guess Michael has sort of answered.
Thank you.
Yeah.
Yeah. I have a question about the B to S plus a dilepton. Am I right in thinking that if you don't put a Q-squared cut, there will be an effect of phase space difference because of different masses of the muon, but the Q-squared cut is to avoid that difference in phase space? Is that correct?
You mean like why we cutting, like for example here in 1.1 Q-squared?
Yeah, I mean, if you don't cut on Q-squared, I would expect a difference because of the mass. The phase space is different for a dielectron and dimuon.
I'm actually not sure of that. My understanding is that the cut at the lower value is to avoid some other resonance that are at the lower Q-square region, like the phi meson, I think.
I see. There is a difference in phase space, right? It may be very small, I don't know, but.
Yeah, I mean, the theoretical prediction depends a lot on the Q-square region that is chosen. So yeah, my understanding is that that region is chosen specifically because like the theoretical prediction is like consistent around the unity over that region, but it will change in other regions.
Yeah. Okay, I think I'm talking about Q-squared min, but okay, all right. Thank you.
Okay, thank you again, Julian.
Thanks.
And we can move to the talk of Julia Negro from CNES. Julia, are you there?
Yes.
Yeah, good.
Yes.
Yeah, can you share your slide?
Yes,
Please.
I'm doing that.
Thank you. Okay, Julia will talk about the top measurements from CMS, and she got her PhD in CMS at Saclay in Paris, and now she's working for the Purdue University for the CMS top quark measurements. In particular, in top quark properties analysis and in combinations of analysis between experiments. So go ahead, please.
Yes, sorry, I will just have to switch off the video because, yeah, I just want to avoid connection issues because there is a huge storm ongoing. So
it's now, Agora. It's good for now, yeah.
Okay. Okay, so I will present the top quark measurements performed in CMS, focusing on a selection of recent results. As you know, the top quark is the heaviest elementary particle discovered so far, with an extremely short lifetime, which allows us to observe the properties of the bare quark, and a larger Yukawa coupling to the Higgs boson, making it an important element in the understanding of the electroweak symmetry breaking. It is also an ideal candidate for spin measurements, since the angular distribution of its decay products preserves the spin information. Thus, studying the properties of the top quark is important to test the internal consistencies of the standard model and to search for new beyond the standard model physics phenomena. The top quarks are mainly produced in pairs at the LIC, where the TT bar production is dominated by gluon fusion, and this can be used to extract QCD parameters, while the single top quark production constrains the electroweak sector of the standard model. Now, the top quark per production rate is very high at the LIC, reaching a production cross-section of around 800 picobar at 13 TeV. And there is an impressive agreement between the different measurements performed at 7, 8, and 13 TeV and the predictions. In particular, the inclusive production cross-section can be calculated up to the next to leading order and next to leading log order in QCD, allowing us to test the perturbative QCD, while the differential cross-sections can be used instead to test fixed order prediction and Monte Carlo generators, providing an indirect search for new physics. The TT bar production is investigated in 3 main channels. So the dilepton one, which has the cleanest signature but a very small branching ratio. The lepton plus jet one, where you need to compromise between the higher signal statistic and the background contamination, and the full hadronic channel, which is significantly less precise because of the large multi-jet background. Then here I present the 2 most recent results on the inclusive and differential cross-section for TT bar production, where in the first one we performed for the first time a combined fit of resolved and boosted topologies, measuring the single and double differential cross-section in the lepton plus jet channel. Where here the boosted top in particular is identified with a neural network approach, and uncertainties are significantly reduced thanks to profile nuisance parameters. So we achieve a good agreement in most variables, but all calculations predict a harder top PT spectrum than the one observed in data. In this analysis, we also measure a total inclusive cross-section that, with its relative error of around 3.1%, is one of the most precise total cross-section measurements. And I also want you to notice this 0 to 1.5 TeV range, which is derived in a single analysis, so not added in different steps, but in a single step, which I think is pretty amazing. Then in the second one, we studied the top production at 5 TeV. So analyzing data in the image channel recorded in 2017 and combining them with a measurement already performed in the lepton plus jet channel in 2015, which are both statistically limited. And the inclusive cross-section shows a good agreement with the higher order prediction, and its precision is a huge improvement with respect to the one achieved in 2015. Then instead, the single top quark production as a cross-section are around 10 to 200 picobar. And again, the different measurements are in impressive agreement with the predictions. And here the three main contributing processes are the T-channel, the W boson production is in association with a top quark, and the S-channel. Then we also have rare processes like the Z-gamma associated production with a cross-section below 1 picobar that I will describe later. The single top quark production is used to measure different parameters, like for example, the charge ratio, with an improvement in precision of almost 4 times with respect to the old 2015 analysis. The spin asymmetry estimated from differential distribution of polarization angle and in agreement with the standard model prediction. And the VTB matrix element derived from the comparison of the measured and predicted cross-section shown here for few analyses. Here instead I present 2 recent results in the TW single top channel. So in the first one, we measure the TW absolute and normalized differential cross-section in the lepton events with a cut and count analysis. So basically we estimate the backgrounds through Monte Carlo simulation and we subtracted from to extract the signal. And we can see that the results are in fair agreement with the prediction within the uncertainties. Instead, in this analysis, we measure the TW semi-leptonic inclusive cross-section, where we perform a profile likelihood fit on the shape of the BDT discriminant that we use to discriminate signal and background. And the measured cross-section that here is compared to other measurement is in agreement with the standard model predictions within 2 sigma. And this is the first time that the TW process was observed in the lepton plus jet channel. Then moving to the top quark mass, basically there are 2 ways to calculate it. So one is refers to as direct measurement, where to extract the mass, we kinematically reconstruct the top quark decay products. And we can achieve the smallest precision we can achieve in a single analysis, which is around 500 MeV, can be improved with combined measurement. So in particular with Atlas and CMS combination, we achieve a precision of around 0.28%. In this analysis, we measure the mass in the single top T channel with lepton plus jet events, which is done for the first time at 13 TeV. And we use a multivariate technique to increase the signal purity and perform a simultaneous machine learning fit to the distribution of the mass. And then we obtain combined measurement of top and anti-top quark masses, which give the first measurement to achieve a subject precision in the mass of the top for a single top enriched event sample. And then we also measure the masses of the top quark and the anti-quark that are in separate way. And this allows us to perform a stringent test of the CPT invariance. And the estimated values of the ratio of the difference between the top quark and anti-quark agree with the unity and 0 within uncertainties. And so we can say that they are consistent with no violation of the CPT invariance. Then another way to get the mass is through indirect measurements, where you measure an observable which is sensitive to the mass, like the inclusive or differential TT-bar cross-section, in a well-defined renormalization scheme. And for example, we can achieve the most precise determination of the top mass in the pulse scheme from normalized triple differential cross-section in the lepton channel. And this we do performing a simultaneous measurement of the alpha strong constant of the mass and the PDFs next to leading order. Then we can also measure the mass of boosted top quarks decaying hadronically in the lepton plus jet channel, where the mass is extracted from normalized cross-section as function of the mass of the jet. And another interesting analysis is the measurement of the running of the top quark mass, which was investigated for the first time, which is extracted comparing the differential cross-section measure in the IMU channel as a function of the invariant mass of the TT-bar system to next to leading order prediction with different values of top mass. Then we perform a maximum likelihood unfolding, okay, we just see that the running is in agreement with the prediction of the QCD renormalization group equation, and that we can exclude the no-running scenarios at above a 95% of confidence level. Then there are a lot of top quark properties that we can study, and here I just mentioned a few of them without going into many details. For example, we performed the Yukawa coupling measurement for the first time in top quark production using the lepton plus jet channel with 2016 data, where the results shown here are in agreement with the full run-2 data measurement, which was instead performed in the dilepton channel, and that achieves an improved sensitivity. Then we also performed the first direct model-independent measurement of the CKM elements in the single top T-channel events, and the first measurement at LEC of the forward-backward asymmetry with values consistent with standard model expectation and in good agreement with previous measurements. Another interesting analysis is the measurement of the spin correlation, where all the distribution and extractive parameters are in close agreement with the standard model prediction, but the delta phi distribution actually shows some tension between data and prediction in both Atlas and CMS. So we perform an Atlas and CMS comparison within the LAC working group, the first one done at 13TV, to investigate this tension. And we can see from this plot that there is actually a very good agreement between Atlas and CMS data and between Atlas and CMS main main Monte Carlo predictions. Okay, for other top quark properties, here I present two most recent analyses. So the first one, we measure the shape of the B quark fragmentation function, where we studied in the lepton plus jet and the lepton decay channels. And for this, we use 3 samples of char meson, and basically we perform a simultaneous fit to the fragmentation proxy distribution XB of this meson that are used as proxy for their parent B quarks. And then we extract the B fragmentation shape parameter RB from these distributions. The results are also compared with the ones obtained at the Z-pole in E+ E- data, which have a completely different color environment. And we can see that the results are in agreement with a significant improvement in the experimental precision with our measurement. And so this basically shows no evidence for an environmental dependence of the fragmentation function. The other analysis is about the search for charge lepton flavor violation done with happen charm quarks and oppositely charged electron muon final states. In this case, we follow a model-independent EFT approach to model the charge electron flavor violation signal. And in particular, we probe separately the EMU-TU and EMU-TC lepton flavor violation interaction using a BDT to maximize the signal sensitivity. And we set upper limits on the signal production cross-section that are then translated into upper limits on the related Wilson coefficients, and then also on the top quark lepton flavor violation branching fractions. That gives up to now the most stringent limits. Okay, so now I move to the rare-trop production modes that became fully accessible with the run-2 data. In particular, we have the associated production of top quark pairs with the WZ and gamma bosons, which are among the most massive signatures that can be studied with high precision and LEC. And we can see their cross-section in this summary plot for TTV results, and also in the bottom plot highlighting in blue. Then we have the TZQ production and the T-gamma Q production, which instead are shown in green in this plot. And in particular, for the analysis of the T-gamma Q production, this was the first time that this process there was the first evidence of this process. Then in these rare processes, we can also do EFT interpretation. Okay, so in particular, the EFT framework is a model-independent approach used to look for new physics processes characterized by a beyond the standard model energy scale much bigger than the energy of the LEC. So the standard model Lagrangian is expanded with an effective field theory Lagrangian with higher order operators and Wilson coefficients which describe the interaction strengths of these operators. So now we can set direct constraints on the top electroweak EFT operators, for example, in the TTZ and TZQ production in multi-lepton final states, where the distribution used for the signal extraction are parameterized in terms of the Wilson coefficients, and we use new machine learning techniques to improve the sensitivity to these Wilson coefficients. Then we do a fit to a single coefficient and also to all the 5 coefficients simultaneously in signal and control region to directly constrain these coefficients. And in particular, the confidence intervals are computed at 95% confidence level, and they are extracted for both the 1-dimension and 5-dimension fit. And this gives the best direct constraints to date from the multi-lepton final states. Then one of the rare top quark processes is the TZQ production, for which we measure inclusive and differential cross-section in lepton plus jet channel, where we perform a simultaneous fit to the BTT output in multiple regions to get the inclusive cross-section. And the results is consistent with the standard model prediction and gives the most precise measurement of this process to date. And then we also perform the first differential measurement of this process, where the distribution of the top and side observables and also of the angular distributions show good agreement between data and next to linear order prediction. Then we also performed the first spin asymmetry measurement in this process, which is found in agreement with the standard model prediction. Instead, we perform an inclusive cross-section measurement in the lepton plus jet channel also for the TTCAM process, where the cross-section is extracted with a simultaneous likelihood fit in multiple regions. And you see the results here. That is in good agreement with next to linear order predictions. And we also constrain 2 EFT operators impacting the T gamma and TZ vertices. And after, of course, performing also the differential measurement that measure the cross-section as a function of kinematic variables of the photon, like, for example, the PT. Then other rare top processes are the TT bar production in association with 2 light jets and 2 bottom or chunk quarks that are shown in blue in this plot. And in particular for these processes, we need precise measurements because we want to improve the simulation of the TT bar plus jet processes, because basically the theoretical modeling of this production is very challenging. And so there are high uncertainties associated to the renormalization and factorization scale affecting this theoretical calculation. Then we have also the 4-top process, it is shown in green here, which has not been observed yet, but is expected in the standard model with a very tiny cross-section. Okay, so to measure the TT-BB cross-section, we perform 2 separate analyses with 2016 data, one in the dilepton and in the lepton plus jet channel, and the other in the all-hadronic channel. And you can see, for example, here that the TT-BB yields are higher than predicted, and while the TT jet yields show a good agreement with the predictions. Then for the first time, we measure the TTCC process with a simultaneous measurement of the cross-section of TTCC, TTPB, and TTGJ, and also of the ratio of the TTCC and TTPB over the TTGJ process. For this, we use dilepton events, and we identify the sequarks using a new C-tagging technique developed exploiting the CJet tagger. And then we use machine learning techniques to perform a template fit to the two-dimension distribution. And from these results, you can see that again the TTBB yields are slightly higher than predicted, while the TTCC and the TTLL cross-section are slightly lower than the predictions. Okay, before concluding, I also want to speak about this interesting effort we are doing within the LISHEP working group about a forced Atlas and CMS common Monte Carlo sample. So currently we use different nominal Monte Carlo sample in Atlas and CMS, which are produced with PAWG and PITIA generators with different parameters. And so understanding the similarities and the difference between these two samples could be crucial to reduce the modeling systematics in analysis combination. And so producing a common Monte Carlo sample would make this combination comparison much easier. So after checking that we could reproduce the main sample from the other experiment in each experiment, we first identified a first set of common settings, and then we successfully produced a first common sample in both experiments. And you can see from this distribution of jet variables that we achieve a very great agreement between the two samples produced independently in separate frameworks. Now we also want to produce a, let's say, real common sample, which is will be tuned on data. And so right now there is ongoing a discussion to decide the new setting to use in this next iteration. Okay, so in summary, a huge number of top quark events was produced during round 1 and round 2. And here I've presented an overview of the CMS measurements with round 2 data, which confirm a good agreement with standard model and allow to explore parameters of the beyond standard model processes. The increased precision is allowed by the large statistic and also by the combination between experiments, providing a better understanding of the top quark properties and also of the physics modeling. And besides, it also constrains new physics processes. And yeah, I also want to highlight again the production of the first common Atlas CMS Monte Carlo sample, which is very long due, and a new version, tuned data, will come soon. Thank you.
Welcome, Julia. Nice talk. Many results that you show to us. One question, despite that we have so many results, is to think about the future. What do you think this collaboration with Atlas, with this common Monte Carlo production, will help with the run 3? What will be the improvements?
Well, the point is exactly to try to improve the modeling systematics in combination. So, for example, I think before the delta phi, yeah, for example, this one for the delta phi comparison, one of the main things is that the systematics are different between the two experiments. So having a common Monte Carlo sample would really improve this interpretation. So the goal is to already have a first sample to be used in this combination in the next months. And then, yeah, the point is that we will produce it for round 3. And then, yeah, for sure it will be useful, so that both experiments can use the same one.
Okay. There is a question from Yara. The question is, I do not know if this is a naive question. Among the top properties, which one would first reveal the BSM contributions?
Okay. Well, this, I mean, for example, in the spin correlation, we also do an EFT interpretation that, yeah, I didn't show here, but I'll probably have a backup slide on that if I manage to get to it. that I think, yeah, I should be almost there. Okay, so for example, okay, you see that we also use, for example, our unfolded results distribution to constrain different anomalous couplings. And so this one could be, I mean, useful for beyond standard model searches. But yeah, I mean, there are a lot of them. Yeah, it depends from the interpretation and the studies that you do.
Okay. Okay, thank you again, Julia, for the talk. And this was the last talk that we have today. Now I can give the word to Santoro again.
Okay. Thank you, Julia. You have the same name, Julia, of my daughter.
Okay.
Okay. Thank you very much for your wonderful talk, and thank you for all talks of today from the speakers, turning this afternoon very agreeable and with a lot of good physics. My friend Harvey, you want to see ciao or?
Okay, ciao. You see, Alberto, I always do what you say.
Thank you. Thank you. Without you, we could not do that.
Anyway, I also found the talks today really great. A lot of wonderful results and really showing how well the experiments are working.
Yes.
Yeah.
Even in this pandemic, we have a lot of good results in physics and prospectus too.
I think absolutely.
Yeah.
Very
Okay.
bright. Okay.
Friends. Okay. And thank you very much for today. And let's do again.